Hey friends, welcome to the YouTube channel All About Electronics. In the previous video, we have seen that how to calculate the RMS and average value for half wave and the full wave rectifier. So in this video, let us see how we can calculate the ripple factor for half wave and the full wave rectifier. And then we will also see how to find the ripple factor whenever these rectifier circuits are used with the RC filter. So first, let us see how to calculate the ripple factor for this half wave rectifier. Now we know that for the half wave rectifier, when we apply a sine wave as an input, then we will get this kind of waveform at the output. So if you observe the output waveform after the rectification, then it is not purely DC output. So basically it is a pulsating DC and it has some finite AC variation in the output. And this periodic AC variation on top of the DC voltage is known as the ripple. And how well the rectifier circuit is able to suppress this ripple is usually defined by the term known as ripple factor. So for any rectifier, this ripple factor should be as small as possible. And it is defined as the ratio of RMS value of the ripple in the waveform to the DC or average value of the waveform. Now we already know the DC value or the average value for this half wave rectifier. So to find this ripple factor, first of all we need to find the RMS value of this ripple. Now for any waveform, the RMS value of the waveform can be expressed by this expression. So from this we can say that the RMS value of the ripple is equal to square root of Vrms square minus Vdc square. Now we already know the DC value for this half wave rectifier. That means Vdc is equal to Vm by pi. And the RMS value for the half wave rectifier is equal to Vm by 2. So if we put these values, then the RMS value of the ripple will be equal to square root of Vm square by 4 minus Vm square by pi square. So from this we can say that the RMS value of the ripple will be equal to Vm times square root of 1 by 4 minus 1 by pi square. And if we calculate it, then this value will roughly come around as 0.386 Vm. So now let us use this value of RMS ripple and let us find out the ripple factor. So now we can say that this ripple factor is equal to 0.386 Vm divided by Vm by pi. And if we calculate it, then the ripple factor for the half wave rectifier will come as 1.21. So in this way, we can find the ripple factor for this half wave rectifier. Similarly, now let us find out the ripple factor for the full wave rectifier. So for the full wave rectifier also, the formula of ripple factor will remain same. So first of all, we need to find the RMS value of the ripple. So like I said earlier, the RMS value of any waveform can be expressed by this expression. And from this, we can say that the RMS value of the ripple will be equal to square root of Vrms square minus Vdc square. Now for the full wave rectifier, this Vdc is equal to 2 Vm by pi. And the RMS value for the full wave rectifier is equal to Vm by root 2. So let us put these two value in this expression. And from this we can say that the RMS value of the ripple will be equal to square root of Vm square times 1 by 2 minus 4 by pi square. And if we calculate this value, then the RMS value of the ripple will roughly come around as 0.3 times Vm. So let us use this value and let us find out the ripple factor for the full wave rectifier. So now the RMS value of the ripple will be equal to 0.3 times Vm. And for the full wave rectifier, the average value is equal to 2 Vm by pi. So if we simplify this expression, then the ripple factor for the full wave rectifier will come around as 0.483. So in this way, we can also find the ripple factor for the full wave rectifier. Now for any rectifier circuit, this ripple factor should be as minimum as possible. And further we can improve this ripple factor by using the RC filter circuit. So first of all, let us find out the ripple factor for the half wave rectifier whenever it is used with the RC filter. So with RC filter, if you see the output waveform of this rectifier, then it can be represented by this yellow waveform. So up to this voltage Vm, the capacitor charges through this diode, and then after it used to get discharged through this resistor R. So due to the charging and the discharging of this capacitor, we will get this kind of waveform. So if you observe this waveform, still it is not purely DC output voltage, and still it has some finite ripple. So before finding this ripple factor, first of all, let us find out the peak to peak voltage of this ripple voltage. So to find the peak to peak voltage of this ripple, we need to find the maximum and the minimum value of this ripple voltage. So once we know these two values, then we can easily find the peak to peak ripple for this output waveform. So in this waveform, once the capacitor charges up to this voltage Vm, then it will get discharged through this resistor R, and during the discharging, the voltage across the capacitor can be represented as Vm times e to the power of minus t by Rc. Now here, let's say the time which is required by the capacitor to reach from the maximum to the minimum voltage is equal to T1. And let's say this T1 is roughly around capital T, which is the time period of this output waveform. And if we put this value in this expression, then we will get the minimum voltage across the capacitor. So the minimum voltage of this ripple will be equal to Vm times e to the power of minus t divided by Rc. Now here we are assuming that the Rc time constant of the capacitor is much larger than this time period. And under this assumption, we can write this minimum voltage as Vm times 1 minus t divided by Rc. Now if you are not aware, we can write this expression using the Taylor series expansion, because this e to the power x can be written as 1 plus x square plus 2 factorial plus so on. And if we assume that this x is much less than 1, in that case the higher order terms can be neglected, and we can write this expansion as 1 plus x. And if this x is negative, that means if we have a e to the power of minus x, in that case we can write this expansion as 1 minus x. So using this expansion, we have written this expression. So this will be the minimum value of this ripple voltage, and the maximum value of the ripple voltage will be equal to Vm. So the Vmax will be equal to Vm. So the peak to peak ripple voltage will be equal to Vmax minus Vmin. That is equal to Vm minus times Vm times t divided by Rc. That is equal to Vm times t divided by Rc, or we can say that this peak to peak ripple is equal to Vm divided by f times Rc. So this will be the peak to peak ripple voltage for the half wave rectifier. And if you want to find the DC voltage for this waveform, then this DC voltage will be equal to the maximum value of the waveform, that is Vm minus half of the ripple voltage. That means the VDC will be equal to Vm minus V ripple peak to peak divided by 2. So this will be the expression of a DC voltage for this waveform. Now usually this ripple voltage used to be in the millivolts, and the peak value of the waveform used to be in volts. So most of the time this second term used to be a very small, and in many cases it can be neglected. So in most of the cases this VDC will be roughly around Vm. So under this assumption, we can write the peak to peak ripple voltage as VDC divided by R times FC. And here this VDC divided by R is nothing but the DC load current. So we can write this peak to peak ripple voltage as IDC divided by FC. So this is the value of a peak to peak ripple voltage in terms of the DC load current. So now as we know the value of this peak to peak ripple voltage, let us find out the ripple factor for this half wave rectifier. So here first of all we need to find the RMS value of this ripple, and we already know the DC value of this output waveform. That means the VDC is equal to Vm minus V ripple peak to peak divided by 2. So to find this RMS value of the ripple, we will use some assumption. Now if you closely observe the ripple in the output waveform, it looks very similar to the sawtooth waveform, because like I said earlier, the value of the ripple used to be a very small. So the charging time which is required by the capacitor used to be a very small. Apart from that, the RC time constant of this filter is much larger than this time period. So during the discharging process, the capacitor almost discharges very linearly. So we can approximate this ripple waveform as a sawtooth waveform. So just by finding the RMS value of this sawtooth waveform, we can find the RMS value of this peak to peak ripple. And for finding the RMS value, we will remove the offset from this sawtooth waveform. So if we remove this offset voltage, then the sawtooth waveform will look like this. So now if you observe this waveform, it is symmetric around this T/2 time period. So we will find the RMS value of this waveform only for the T/2 time period. So before finding the RMS value of this waveform, let us write down the mathematical expression for this waveform. So this waveform can be expressed as Vm minus 2Vm by T times T, and this expression is valid for 0 to T time period. So in this expression, if you put this T as 0, in that case this V of T will be equal to Vm. Similarly, if you put this T is equal to capital T, in that case this V of T will come as minus Vm. And likewise, if you put this T as T/2, in that case this V of T will be equal to 0. So this mathematical expression represents this waveform. So the RMS value or Vrms square can be written as 1 by T/2 integration 0 to T/2 V square T dt. So if we put the value of V of T, then this expression can be expressed as 2 by T integration 0 to T/T Vm minus 2Vm by T times T whole square times dt. And further, if we simplify this expression, then we can write it as 2Vm square by T integration 0 to T/2 1 minus 4T divided by T plus 4T square divided by T. So if we integrate this expression, then Vrms square will be equal to 2Vm square by T multiplied by T minus 2T square divided by T plus 4T cube divided by 3T square with limits from 0 to T/2. So if we put these limits and if we simplify this expression, then the Vrms square will be equal to 2Vm square by T multiplied by T/2 minus T/2 plus T/6. So we can say that the Vrms square will be equal to Vm square divided by 3. That means Vrms will be equal to Vm divided by root 3. Or we can say that it is equal to 2Vm divided by 2 root 3. Now if you observe over here, this 2Vm is nothing but the peak to peak voltage. So we can say that this Vrms is equal to V peak to peak divided by 2 root 3. And if we compare this sawtooth waveform with the peak to peak ripple, then we can say that the RMS value of the peak to peak ripple will be equal to V ripple peak to peak divided by 2 root 3. So now once we know the RMS value of the ripple, then we can easily find the ripple factor. So this ripple factor is the ratio of RMS value of the ripple to the DC value. So here this RMS value of the ripple is equal to V ripple peak to peak divided by 2 root 3. And like we have seen, this DC value of the waveform is equal to Vm minus V ripple peak to peak divided by 2. Now for the half wave rectifier, we have already seen that the peak to peak ripple can be expressed as Vm divided by R times Fc. So the numerator can be expressed by this expression. And similarly, by putting the value of peak to peak ripple, the denominator can be expressed by this way. Now here we are assuming that the RC time constant of the filter is much larger than this time period. And due to that, this second term can be almost neglected. So under this assumption, this ripple factor can be written as Vm divided by 2 root 3 times R times Fc divided by Vm. Or we can say that the ripple factor for the half wave rectifier will be equal to 1 divided by 2 root 3 times R times Fc. So this will be the ripple factor for the half wave rectifier whenever it is used with the RC filter. So similarly, now let us find out the ripple factor for the full wave rectifier. Now whenever the full wave rectifier is used with the RC filter, then the output waveform can be represented by this yellow waveform. So here before finding this ripple factor, first of all let us find out the peak to peak ripple voltage in this output waveform. And like we had seen in case of half wave rectifier, first of all we need to find the maximum and the minimum value of this ripple. So for finding that value, first of all let us assume that this time is equal to time t1, which is the time which is required by the capacitor to reach from the maximum to the minimum value. And during the discharging of this capacitor, the voltage can be expressed as Vc of t is equal to Vm times e to the power of minus t divided by Rc. And if you put the value of t as t1, then we will get the minimum value of this ripple. That means V minimum is equal to Vm times e to the power of minus t1 divided by Rc. Now here this time t1 is approximately equal to time t by 2. So this V minimum can be expressed as Vm times e to the power of minus t divided by 2 times Rc. And further, this Rc time constant is much larger than this t by 2 time period. So under this assumption, this minimum voltage can be expressed as Vm times 1 minus t divided by 2 Rc. So this will be the minimum value of the ripple voltage, and the maximum value of the ripple will be equal to Vm. That means Vmax will be equal to Vm. So if we take the difference of this Vmax and Vmin, then we will get the peak to peak ripple for the full wave rectifier. So the peak to peak ripple voltage can be expressed as Vmax minus Vmin. That means peak to peak ripple will be equal to Vm minus Vm plus Vm times t divided by 2 times Rc. Or we can say that the peak to peak ripple is equal to Vm divided by 2 times Rfc. So this will be the value of peak to peak ripple for the full wave rectifier. And the DC value of this output waveform can be expressed as Vm minus V ripple peak to peak divided by 2. And if you want to express this peak to peak ripple in terms of the DC load current, then it can be expressed as IDC divided by 2 times Fc. So this will be the value of a ripple factor in terms of the DC load current. So now once we know the value of this peak to peak ripple, then let us find out the ripple factor for this full wave rectifier. And for finding this ripple factor, we need to find the RMS value of this ripple voltage. And for finding this RMS value of the ripple, once again we will use the same assumption. That means the variation in this ripple voltage is same as the sawtooth waveform. So just by finding the RMS value of the sawtooth waveform, we can find the RMS value of this ripple voltage. And for finding the RMS value of this sawtooth waveform, we will neglect this offset voltage. So by neglecting this offset voltage, the sawtooth waveform can be represented like this. Now here, before finding the RMS value of this waveform, we need to express this waveform in the mathematical form. And in mathematical form, it can be expressed as Vm minus 4Vm by T times T. And this expression is valid for 0 to T by 2 time period. Now one more thing, if you observe, this waveform is symmetrical around T by 4 time period. So instead of finding the RMS value for this entire T by 2 time period, we can only consider this portion. So for this waveform, the Vrms square can be expressed as 1 by T by 4 integration 0 to T by 4 V square of T times dt, where this V of T is equal to Vm minus 4Vm by T times T. So I will encourage all of you to find the RMS value for this waveform. And if you put the value of V of T from this expression, and if you go through the procedure that we had gone for the half wave rectifier, then you will see that the RMS value will come around as Vm divided by root 3. And like we had seen, we can also represent it as a 2Vm divided by 2 times root 3. And here this 2Vm is nothing but the peak to peak voltage. So we can represent this RMS voltage as V peak to peak divided by 2 root 3. So from this we can say that the RMS value of the ripple will be equal to V ripple peak to peak divided by 2 root 3. So now once we know the RMS value of this ripple, then we can easily find this ripple factor. So by putting the RMS and the DC value of the waveform, we can write this ripple factor as V ripple peak to peak divided by 2 root 3 divided by Vm minus V ripple peak to peak by 2. And if we put the value of the peak to peak ripple for the full wave rectifier, then the ripple factor can be expressed as Vm divided by 2 root 3 times 2 times F times RC divided by Vm minus Vm divided by 2 times FRC. Now, like we had discussed for the half wave rectifier, here the RC time constant of this filter is much larger than T by 2 time period. So under this assumption, the second term can be neglected. So from this we can say that the ripple factor will be equal to Vm divided by 4 root 3 FRC divided by Vm. And if you further simplify it, then the ripple factor will be equal to 1 divided by 4 root 3 times F times RC. So in this way, we can find the ripple factor for the full wave rectifier whenever it is used with the RC filter. So I hope in this video you understood how to find the ripple factor for the full wave as well as the half wave rectifier. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.